Greetings, this is Artie from Artifact Electronics. Today we're going to fix another PCB. I went through my parts board stack and I found these two guys. The initial diagnosis is purely based on visuals, and as we can see they both got parts missing over here and over here, and there's also circuit board burn damage, which I'll show you a little closer later on. But let's see if we can make one of these work. They're both dead. One's going to live and one's going to stay dead. What I'm going to do is use parts off of the one that is not going to get fixed, parts that I don't have, in order to replace parts with all of the stuff missing here or here. I'm just going to pull it off the other board if available. Now this one's pretty sparse as far as parts are concerned. This one's better. So just having an initial look at these guys, make a guess onto which one of these boards is going to get revived. So what do these do? I've briefly talked about them in previous episodes. I actually fixed one of these where I think in the Whitewater Pinball the display was missing a column and just didn't look right, but when we ran the diagnostic it pretty much told us that there was a RAM error on there, and all we had to do with that board was replace the RAM, which is over here. It's an 8K static RAM, and that fixed that. But that error is not as common as, or defect is not as common as what you see on here, and let's briefly talk through what they do. So we have a digital part, which is all these TTL chips and the memory, and the processor talks to them through these connectors, and essentially this is the display, the logic part of the display. It's a frame buffer. The CPU writes data into the SRAM, and then the rest of the circuitry picks it up and sends it out dot by dot to the dot matrix display, or DMD for short. But this is a full driver board in that it also generates the voltages required for the DMD to function. And those voltages are, we look at this, we have plus 62 volts over here, we have minus 125 and minus 113, and also 12 volts. So the display needs all four voltages to function correctly. It's a very simple setup using we have the AC coming in from the secondaries of the transformers. It is rectified, and then basically using these pass transistors over here with Zeners as voltage references to generate the appropriate voltage. And this guy, the minus 113, basically leaches off of the minus 125 volt regulated display, and using a 12 volt Zener drops it. Is that 125? Yeah, I guess the math doesn't make sense. Well, no, it does. 125 minus 12 is 113. So it's really a simple, classic, not very efficient setup. But I think what they did was, this stuff is under spec because, as you saw in the burn marks on the board, these things are on 24, or were on 24/7, and they just got really hot. Also, the DMD displays, as they age, tend to draw more current. So with all of that in mind, the boards just disintegrate. I mean, the power portion of them just disintegrates. So that gives you an idea of what we're looking at. And obviously on both of these, the voltage regulation circuitry has gone bad. And that's where we have to replace all of the parts in. But we need to make the determination of who comes back to life. So let's have a, and again, the diagnosis right now is purely visual, based on visual cues, but we can look at this. A lot of burning on this side. A little bit of burning over here. Not much going on as far as damage there. And if we look on the back, it looks pretty nasty. Pads missing. There are pads that are completely, they're completely gone dull, which means the heat, they were just heated up so much that, I got to clean this up, of course. But yeah, that's really, that tells you what this one looks like. And then if we look at this one, has the same kind of damage over here, except somebody took out all the parts. Whereas, we can see down here the board's still pristine. But again, because of this damage over here, I guess somebody decided that this was unfixable and start pulling parts and hopefully fixed another one. But there's one big thing I didn't show you that I didn't even notice in the beginning, and that is there's 2 TTL chips missing on this one. So first thought is, well, they probably were bad on another board, and since this was bad over here, they made a decision to pull these parts off and use them in another board. But no. If we look on the back, and we see this discoloration here. The discoloration that we see over here can be explained by the regulators getting really, really hot. But these are TTL chips. They should not be getting this hot to discolor the board. And one thing, you can't really see, the board actually, the PCB bulges over here. So there was a catastrophic failure, at least on this chip, probably on this chip too. So what that means is we may have a bunch of logic problems in here. If these 2 guys blew up, how many of these did they take with them? So I guess you can already guess that even though initially looking at it, it would seem that this is the one that gets brought back to life because it has more parts on it. But no, because of that TTL issue over here, she's going to live, and she's going to stay dead. So the first thing we need to do is clean up. We need to clean up as much of this burn stuff, see how many of the pads we can bring back to usability. Also looks like somebody took off the solder mask here. You can see the copper showing through. Maybe somebody already thought of repairing this, but then abandoned the idea. So I'm going to go and clean this up a little bit more so I can actually see if a copper trace, if it makes it to a pin or if it's burned off. And once we put this back together, put the parts in, and it works, we need to put some sort of solder mask back on these. I don't want to leave them bare. They do sell solder mask on eBay, but I think that's kind of stuff you put on here and then you have to have a UV lamp for it, and it tends to look pretty ugly. What I'm going to do is something that looks a little bit less ugly and it's probably also cheaper, and that is from your local dollar store. You can get rapid dry top coat for fingernails. And it's basically varnish that dries clearly, and it dries rapidly too, so you don't have to wait for too long. But anyway, once the board works, I'm going to cover all the exposed copper with this, and then we have a board that looks like it just came out of the factory. So here's what it looks like after cleaning up. I used the IPA first, but it didn't do anything at all. So I used some acetone, and the acetone brightened things up a little bit, but didn't do that much either. But you can clearly see the orphan pads over here with no traces on either side, and just cool stuff like that. So I guess I'm going to start transferring over some of the parts that I don't have from the parts board, and then dig through my own parts for the stuff that I think I know I have. So I only use the highest quality acetone. Also comes from the dollar store. Nail polish remover, 100% acetone. So works good, feels real good on your hands, makes your skin turn white. It's good stuff though. It works really well. So, oh yeah, I did do a little work on the other end. Also cleaned it up, scraped it. Didn't make a lot of difference. And I transferred this resistor. Of course, any part that gets transferred gets tested first. Also, this capacitor that sits on the 12 volt line. And again, if you've seen previous episodes, these blue Phillips capacitors don't seem to age very gracefully. Even though the value on this one wasn't too far off, but it was showing an ESR of like 20 ohms. So, bye-bye. So let's start digging for parts and populating this thing. Alright, we're making some headway here. Caps got transferred. I hear some of you groaning, why do you put in 25-year-old capacitors? Because I don't have any in stock right now, and I want to get this thing done. I tested them. Everything looked good on them. I know they're old. I know they're stressed. I know these are 85-degree parts. So fine, you know, next time I buy parts, I'll buy the real parts. But these are good, and they're back in. All of this stuff got replaced. Stuff over here got replaced. So to have a look at what we have here, these are new. This got transplanted, the resistor, new. This one, geez, I don't remember. No, this one was actually on this board already, so I measured it and it was good. That's a Zener. It's just a rectifier diode, new one. Jumper is brand new over here. And these two were also on the board, but no damage. Further on, these two transistors are new. The resistor was on here, and two 56 volt Zeners are new. And looking at the other side, it really wasn't that bad. After I guess I cleaned it up, the only jumpers I've found I needed so far was the one diode, which had the basically the holes with no pads and burned through. But I connected one leg to where it goes and then the other leg to one of the transistors. Plenty of space. Between here and here. So what remains are the big transistors, the pass transistors, and the heat sinks. And that's what we'll do next. This next segment is specifically for members of the ITPP, the International Thermal Paste Police, and I'm going to show you how to apply thermal paste. See, a while ago I was caught red-handed putting on too much thermal paste on a repair, and was accused of destroying the board, and I guess, you know, the only just punishment for that would have been whipping me or something. But I have since mended my ways, and I shall show you the proper way to do this. I will use Protonics thermal paste, one of the cheapest I could find on eBay, and here is one of the pass transistors. I shall use a toothpick with a dulled end. I cut off the sharp part. Apply sparingly the thermal paste. Oh, here he goes again. Look at that. A beautiful coating of thermal paste. And then proceed to insert it into the heatsink. Uh-oh. Bring it down a little, so otherwise the legs will be too short. And look at that, I'm making a royal mess already. Apply the nut, but don't tighten it yet. That way you can adjust. Oh my God, look at that. Look at all that wasted thermal paste. And we then take the board and insert the whole thing. And we get enough of the pin sticking out on the other end. And there you have it. Absolutely beautiful. So I'm really curious about what kind of comments I'll get on this. But I just saw something else very interesting. Look at this pin. Looks like somebody inserted the connector at one point and was in a rush and just shoved it in there, and the pin missed the hole in the connector. So, I'm sure that caused a lot of heartache when the display was going bananas. But I'm going to go repeat that for the other two. This one is a brand new part, the transistor. It is a MJE 15030. And at that point, we should pretty much have everything on the board. For the remaining two transistors, I'm going to use recycled parts. Why? Because I have them. We're going to test them, of course, but these MJE parts aren't that easy to come by anymore. So I'm going to use these. Now, the first one is an MJE 15031, which is a complementary to the 30. This is the PNP part. So let's hook it up and see what the tester tells us. PNP is a beta of 160. Looks fine. This one's going in. And the next one is, again, like the first one, is an MJE 15030. But oh horror of horrors. Can you see that? It's an NTE part. NTE makes general purpose replacements for all sorts of semiconductors, but I've mostly had good luck with it. I've gotten some TTL chips, actually some CMOS chips that were not performing very well. But since they usually have one transistor to replace a whole bunch of others, these things are usually over-spec'd for the transistor you're using. So let's see, this is or should be an NPN. And if it shows good, this one's going in too. Guess not. This one's a PNP. So this is actually an MJE 15031, not a 30. So even though it's good, yeah, I even got the bag labeled. So I'm going to have to take an 030 out of my stock of parts for that, and we shall continue putting those in. All right, the deed is done. They're all back in. There you go. The only problem I had with this was the heatsink has these tabs that get bent over to hold them in place. But the heat sinks are made of aluminum, and I guess they're not made to have these tabs bent a couple of times. So most of the tabs have broken off, and essentially the heat sink's held in place by the transistor. But that's best we can do right now. Next step, the big test. 24 hours have passed since the last clip. I got tired of it last night and thought I'd test it the next day. Of course, this morning a lot of work was to be done, and anyway, around lunchtime I had some time and I thought, let's test this out. I had little time, so I didn't set up the camera. I just plugged it in, started measuring voltages, and I heard a crack, fizzle, and pop, and saw magic smoke rising from the board. So the universe punished me right off the bat for not sharing. But anyway, later at night now, and I've had some time to go over it, and let me show you what I found. So I went through the whole thing and identified where the smoke was coming from. And the smoke was coming, let's see, from this resistor over here, 120 ohm half-watt resistor. And I started checking things, components and everything. I even took out the big transistor over here, and everything was good except one of the little guys. And this guy, it's a 2N5551 NPN. He was bad. So I replaced him. He is in there. right here. And now you ask, what is this monstrosity? Well, as I was trying to fix it, I had a gazillion 120 ohm resistors, which is what that is supposed to be, but they were all a quarter watt. And this needs to be a half watt, and since this was smoked, I didn't think it was a good idea to put in a quarter watt. So I made a resistor from 100 and a 20, and it actually measures, it's like an ohm and a half low, but everything seems to be back in order. Well, back in order, back to the way it was before. Of course, I had to work on the other side, because of course the resistor that burned up was part of the jumpers I put in, and I had to remove all of that and redo it. But it's back, it's pretty much back to where it was. But then I had to find out, why did this thing smoke? So let's look at the schematics. So I had to double check everything again for connections. Yesterday I did it kind of quickly, and obviously haste makes waste. I overlooked something. So I started measuring stuff. This is the resistor that burned up. And Q10, where's Q10? And Q10 is the one that also blew up. So I looked through the whole thing. I started buzzing out all the connections, and the check marks mean, yeah, they're good. And then I got down here, and lo and behold, there was no connection between here and here. So this feeds the base of this, which in turn regulates what's going on over here. Since this was cut off, this just ran away and blew itself up. And as a result, I guess a lot of current, because this was obviously in breakdown, the Zener over here. And since this couldn't regulate it, this transistor couldn't regulate the current here, I think this just went bananas, and somebody had to absorb the extra voltage that was showing up across this. And that was this guy. And he gave his life. Burned up. I measured him. He still was like 30 ohms or something like that. But I turned off the machine pretty quickly. It didn't get a chance to smoke for a long time. But I think that's what happened. And then, of course, checking the board. Yes, there was a trace that was completely vaporized. I thought I tested it, but this trace was gone. So I put in another jumper to connect this to here. And if we look at the back of the board, you may have noticed that I have a 0 ohm resistor over here to make the missing connection. And the reason I use this is when you use wire, insulated wire, to make jumpers on the back, usually the insulation doesn't contain any Teflon. And even if you cut it to size and have the ends stripped, and then the minute you solder it in here, the insulation shrinks away from you because of the soldering heat. So I tried like 2 times, and by the time I had a good connection, the insulation was gone. And then I remembered the infamous 0 ohm resistor, which was perfect for this application. Doesn't look too clean, but I checked it, nothing touches nothing that it's not supposed to. And remember, we're going to varnish this, if of course it works. But that kind of adds up the fixes I made. And oh, there was another fix. Well, I don't know if that would make a big difference, but what we're looking at here is we got 12 volts coming in here from the connector. That's coming from the driver board. That is already 12 volts. It's already regulated. But then they drop it by 0.6 volts over here, and then it says 0 ohm jumper. And that was a jumper I had in there. And then there's a Zener diode going to ground over here, and it says no part. So I guess my mistake was I saw the 0 ohm jumper and I put in just a jumper, piece of wire here, and then as I was looking over the board I realized that this diode that says no part was actually installed. So the way this works is this is 12 volt, this is over voltage protection for the 12 volt supply, which is kind of strange because it's coming regulated from the board already, but I guess they wanted to make sure that the 12 volt doesn't go bananas over here. And the way this works is basically under normal conditions, this is a 12 volt Zener or a 12.5, or I'm not sure exactly, but it's in the 12 volt range. And what happens under normal circumstances, if the voltage is okay, this is just an open circuit, and we got our 12 volts here. But if the 12 volt rises, the Zener goes into reverse breakdown and tries to clamp the voltage at 12 volts. Now, when you have the Zener here, you have to have a resistor here, because if you don't have the resistor, there's nothing to absorb the extra voltage, and this thing will blow up on you. So what I did was, on the good board on the existing board I had, I measured, there was a resistor in here, and it was, what was it, 57 ohms? Something like that. So it was a 57 ohm quarter watt. So I installed that, which is over here. So that's in there. I mean, that didn't really, I don't think that hurt anything when I put it in, but it would have hurt things if the voltage ever rose above 12. So that got changed, that got fixed. So now it's really time to plug it in. Only the transformer secondaries at first, over here and here, and then this is what goes to the display. And what we're going to do is measure voltages over here and see what's coming out of this. Well, and of course see if it's going to start smoking again. Alright, the board is in. Over here, of course. And really all I've done is plugged in the transformer secondaries that feed this board here and here. This isn't connected. The digital connectors are floating in the air. So all we're going to do is test some voltages. And of course, look for magic smoke. So far, so good. Now, one thing to remember is you have to take the voltages with a grain of salt. If you've seen previous episodes, they seem to take some liberties with how they list their voltages, the DC voltages, because I was working on a solenoid problem, and the solenoids are fed by something that the schematic says is 50 volts DC. Every single machine I've seen actually feeds 75 volts to the solenoids. So I think there may have been changes that never appeared in the schematics. So I expect the voltages we see at this connector, this is the connector that feeds the dot matrix display, I expect those to probably be off. So let's have a look. Pin 8, supposed to have 62 volts. Hello. Alright, that didn't work. I'll tell you what, I'll leave the meter down here and you'll just have to trust me. Okay, it's reading 60. I can't even see it, that light's blinding me. saying 66 volts. Now, one of the things I did was I measured the voltage in the working board to compare, because of the reason that I don't really trust what the schematic says. And that one was showing 65 volts on the 62 volt line. So we should be good over there. Pin 7 is 12 volts. Yeah, let's see if I can short them now and destroy it. 12.28, and that's okay. Pin 6, VCC, which I'm guessing is the digital 5 volts. That's showing 4.86. That's good. Of course, we have ground here and here. And then we get to pin 2. Where's pin 2? Pin 2 is supposed to be negative 113. And that shows negative, come on, cool, calm down. It shows negative 97, which is in line with what the good board showed. Also, these voltages are probably going to be different when the display is plugged in, because it's running under a no-load condition right now. And the last one, pin 1, is supposed to be minus 125 volts. That's also going to be low. It's minus 120 volts. And again, that's in line with what the good board that used to be in here showed. So with all of that checked, no smoke emitting, no sparks flying, and no extreme heat coming off anything yet, I think it's time to plug in the rest and see what happens to the display. Alright then, everything is plugged in now. And let's see. Let's get rid of some more of these lights. And off we go. There you go. We got a working display. So let the machine tell us. Run the test patterns, test the RAM, and see if this board actually is back in play. So, testing the columns. Followed by the rows. Everything looked good there, everything lit up. Doing the inverse screen. Looks happy so far. Diagonals, grid, and testing the RAM. What do you say? Looks like we got a working display. Well, display driver board. So I'm going to let this run for a while. Call it a burn and test for the new components. And I'll go in and check voltages again after a little while and see if they're more in range right now. But again, the voltages are very close to what came out of the board that was in here already. So I'm not too worried about it. But yeah, let it run for a while and then we see what gives. So she's been running for a while. The display is still happy. I went in and I measured the voltages again, under load this time, at the connector. And they really haven't changed a whole lot. So what could be causing this? I mean, the idea is that when these things were new, they were putting out something close to what the schematic specifies. And after thinking about this, the problem is, yeah, okay, I'll close it. So here's a donor board, and as you saw before, the area is really ugly. It's burned up, it's black. And we look at the other side. There's a lot of discoloration going on here. Now, you can call them burn marks, heat marks, whatever you want. But what we're looking at is carbon. And carbon is conductive. Need I say more? Well, we got a whole bunch of random high resistance values, high value resistors, represented by that black area, that are making connections or introducing resistance that was never intended. And as the board ages and gets toasted more and more, you will see the voltages drift because of parasitic resistance all over it. So that's my theory on this. How can you fix it? You can't really fix it on an existing board because it's impossible to remove all the carbon. You need a clean board to get it to perform as it was intended to. But this seems to work fine. This has been running for a while. The voltages aren't that high or low. The display is obviously happy, so I think we got a successful repair and saved another display board from the landfill. So thanks for watching. Leave me a comment and maybe a thumbs up. And I hope you enjoyed this. We'll see you next time.